Yes, tonight we are going to look at MP completeness. And the reference book for this topic is Computers and Intractability, a guide to the theory of MP completeness, a 1979 book authored by Gary and Johnson, W.H. Cole are the publishers. Now we look at the general problems. And this general problem is going to be considered in line with the input size and the time complexity. We know that time complexity of an algorithm is an important feature, and our concern is about having an efficient algorithm that performs optimally. That's the problem in a record time. Therefore, there are two considerations from the time complexity. The first consideration leads to efficient algorithm, while the second leads to an exponential time algorithm. Again, the first leads to an efficient algorithm, and the other will give you an inefficient algorithm. So, if we consider these two scenarios, there are two possible categories for the efficiency of that. One is an algorithm that solves a problem in the polynomial time. And the other one is the algorithm that solves a problem in exponential time. I will take time to explain this very clearly. If you look at what I have here, I said I am going to use the input size to discuss the complexity of an algorithm. So here we are looking at the input size as 10, the input size as 30, the input size as 50. Now for n at 10, it takes 0.00001 second. This is small enough to allow us to say the algorithm is efficient. But you cannot determine if an algorithm is efficient considering just an input size. The stability and the efficiency of an algorithm is large. So you cannot use a small use to determine or classify an algorithm. You would rather use the input size that is larger than the default input size. So that will help you to understand the performance of that algorithm as the input size increases. You understand that you do not need a program. You do not need an algorithm if your input is small. You will not use a calculator to multiply 2 by 2. However, when you need to multiply 2 by 2,025,000, you need a calculator because the input size has increased and so on and so forth. So if you look at what we have here, this is the linear time, this is the polynomial time, and 2 to the power n is the exponential time. So you see that for the linear time, at the input size 50, you have 0.000005 seconds. At the polynomial time is 5.2 seconds, 5.2 minutes. And at the exponential time is 34 for the same input size. So it means that this exponential time is inefficient. It is an inefficient algorithm, while the polynomial time is considered an efficient algorithm. Like I said earlier, you do not need an algorithm. You do not need a computational process. If the problem is easy, it's now measured as a scheme to solve hard problems. But let us even look at what we call easy or hard problems. Problems are divided between two clear lines. It can be said to be easy or it can be said to be hard. For example, if you have a graph, you have drawn your graph and you want to find the shortest path between x to y. All you have to do is to look at a point in x to y and the shortest path that takes you from x to y. But when you want to talk of the longest path in that same graph, x to y, with no circles, that is, there are no connections, then it is a hard problem. We can from the weighting. If there is a simple path from x to y, less than equal to m, then we say it is easy. But if that is greater than or equals to the benchmark, it becomes hard because there are several values. There are several values that will exist when the weight is greater than or equals to m. So the first one can be classified as a polynomial time problem. And the other one can be classified as the exponential time problem. All known as polynomial time problem will always take an exponential time and therefore becomes very inefficient. So we can perform this operation again and again and again. But of interest is the use of an example called the binary search to get the optimal profits. Because you don't get the optimal solution to a given problem. And this problem is generic as an optimization problem, generally known as the knapsack problem. But what is a knapsack problem? The knapsack problem is a form of a decision problem. The solution to a decision problem will either use a most optimized decision problem because of their time complexity. I'll show you an example and explain to you what we mean by a knapsack problem. The knapsack problem is a problem that is used in combinatorial optimization. It is used in combinatorial optimization. Items. You have a set of items, each with a weight and a value. You want to determine the number of each item to include in a collection so that the total weight is less than or equal to the given limit and the total value is as large as possible. I take it again. It is a form of a combinatorial, and what it does is that we want to measure that if you have a set of items that has a weight and a value, we want to determine the number of items that can be included in a collection such that the maximum weight did not exceed the weight of that collection, and you are taking the highest value that is permissible for that collection. That is a knapsack problem. So assume that we have a decision algorithm X for a with capacity M. So we say the algorithm X returns yes or no to the question. Is there a solution with a profit? Profit is when you have greater than or equals to P subject to the knapsack capacity. That is, the number of items that can be included in that collection is greater than or equals to P subject to the fact that you do not exceed the capacity. And if you remember what I told you about knapsack problem, I said this is a problem. Give example, like give a clear example that makes you understand the knapsack problem. And I know you know what we call a knapsack. That backpack that you put behind you and your laptop bag is an example of a knapsack. What we are saying is you have items, you have small items, 2 kg item, 1 kg item, 3 kg. You want to put all of these items, your book, your laptop, your pen, your food flask, your everything inside that knapsack. The problem is the problem of solving what is the maximum weight that you can put, that you will not exceed the 15 kg, that is the maximum capacity, and that you will be able to add as many items, as many books as you're supposed to bring to school. You'll be able to add them into that bag. And that's why we said that it is a combinatorial optimization problem. Combinatorial is that you are bringing several values, you are combining them together, and you are still trying to see that you do not exceed the capacity of the bag, while making sure that you have added into the bag as many values as possible. That is the example of a knapsack. So if this is given as the expression for the knapsack problem, we want to search for the optimal profits between the boundaries of the lower band and the given upper band, which is between 0 and all summations of the profit, which is the PI, the P values, which are the profits. So the profit at every given point is added together to give the maximum bound for that problem. And that takes us to the classes of E and NP. We start by understanding the class P and the deterministic Turing machine. So if you are given a decision problem X, if there is a polynomial time deterministic Turing machine program that solves X, then X belongs to P. Given a decision problem X, so you have a decision problem. For example, the knapsack problem is a decision problem. So if you have a problem like that that has to do with optimization in the result based on some constraints. So you have an objective function and you have some constraint that satisfy the objective function. So if that is correct, then we say there is a program, a polynomial time deterministic Turing machine program. So we know that polynomial time solves a problem efficiently. So if you have what we are saying here is that if you have an efficient program that solves the decision problem X efficiently, then X belongs to P. In polynomial time algorithm to solve the problem. So we say that for that class of problem, it's a polynomial time algorithm that solves that problem. Now let's look at the class NP and the non-deterministic Turing machine. We see even the same problem X. If the polynomial deterministic Turing machine program that solves X, then X belongs to NP. Remember, when it is deterministic, it belongs to P, and when it is not deterministic, and we say, as an example, given a decision problem X, for every instance of I in X, you get solution X for I, and check if S is a solution to I. If A and B can be done in polynomial time, then X belongs to NP. You see that this problem now is a non-deterministic Turing machine program. This kind of guess is unlike what you have here that solves the problem in polynomial time. When it is the program that solves the problem is a non-deterministic program, then the X belongs to the class called NP. Or if it is solved by deterministic Turing machine, it belongs to P. So what we're seeing here clearly is that P, the problems that are solved in P, X so that solved by P is either a subset or equal to those that solve in. Because if you look at it, we said that for every instance of I in X, so it means that this problem X and it is polynomial time. Here, we said that the problem, if a problem is solved in polynomial time, it belongs to a class P. So it means that class P here is a subset of the classes of NP. That is, a decision problem in P does not need a guess solution. This correct solution can be computed in polynomial time. So this is what we have here. So you see the P and you see NP. So in this, with the class of this, you have P as a solution because of the problems which are in NP but may not be in P. And that is what we have. If you understand circle very well, this is clear that some problem will be in NP but will not be in P. For example, 0/1 knapsack problem. The partition problem, which is given a set of positive integers Z, is there a subset of Z prime of Z such that sum of all the numbers Z prime is given as Z minus Z prime. And the solution is a partition problem that divides the constraint into their respective objective functions. So one of the most important open problems in theoretical computer science is to find if P equals to NP. Most times it is not. We have not found problems that guarantees that P is equals to NP. Rather, we have seen problem that says that the problems that are classes in P are also solvable in NP. Make P a subset of NP. So there are many non-decision problems in NP. However, there's no solution to show that any one of them is in P. So the NP complete. So we have talked about P, we have talked about NP, now we are on NP complete. Stephen Cook introduced the notion of NP complete problems. This makes the problem P equals to P, NP. And these are the things that are presented by Cook. There is a transformation for L1 to L2. And this interprets that there is a polynomial time transformation that transforms the arbitrary instance of L1 to some instances of L2. So therefore, if L1 and L2 exist, then L2 is in P implies L1, or L1 is not in P implies L2 is not in P because there is a transformation. This sign is called the polynomial transformation. It means that we have transformed L1 to L2, and that's why we are saying that if L1 is transformed to L2, then L2 is in P implies that L1 is in P. This is straightforward. This is transformation. So if we transform L1 to L2, if L2 is in P, it will imply that L1 is also in P. So if L1 and L2 and L2 and L3, if L1 is transformed to L2 and L2 is transformed to L3, then it means that we have transformed invariably L1 to L3. So when you focus on the class of M, you have many intractable problems, and this problem belongs to a class. L is NP complete if and only if L is an element of NP, and 2, for all other variations of not L, that is elements of L that are in NP, the L prime can be transformed to L. We have L that is a member of not NP, and we have that this is one condition. The second condition is that prime, that is all other values in that set that is not L, are also elements of NP, such that the L prime can be transformed into L. If this is possible, then the class of that such problem is called the NP complete problem. So if an NP complete problem can be solved in polynomial time, then all the problems in NP can be solved in polynomial time because of this transformation. If an NP complete problem can be solved in polynomial time, because it has transformed to this, then all other can then be solved in polynomial time. If a problem, all other NP problem cannot be solved in polynomial time. We have to note that NP complete problem is one of the hardest problems in the NP concepts. L is NP hard. L is NP hard if for all other values of L that are not in L, that are also existing in NP, then for all other NP prime, which are elements of NP, L prime is also transformable to L. And that justifies that if you look at it here, this is the NP. So once this NP exists, every other values of L here are transformed into L. So once this is complete, then we can say that it is an NP hard problem. Of course, the NP hard problem is a problem which is as hard as NP complete problem, but does not necessarily have to be a decision. So, being as it may, we found that an NP problem is in P, then it is just same as it's in NP. If P is not equals to NP, that is, if the problem has a class that is that is not NP, a class P that is not equal to NP, the problem are in NP minus P because it's not equal to NP. It means that they are just in other classes except the NP minus P. That is the distinction between NP and P. So we now have a task that how can we obtain the first NP complete problem for L? That is contained in the Cook's theorem called satisfiability in NP complete. And that had to do with instances and classes. Instances and classes. Instances and classes will give you a variation of the variables, will give you a variation of the clauses over the same given set. To give you a variation of the variable, give you a variation of the classes over the same given set. So therefore, it is important to note, just have like 4 minutes more. It is important to know the variations and the classes of problem that these algorithms are categorized for such solutions. Now, we have an interesting part here that you look at the examples of the conjunctive normal form is the product of sums. And this is a transformation of the conjunctive normal form. The transformation is that even for a given set, you have the set to have two elements, x1 and x2. But we are saying that we are introducing a C, which is a conjunction. The conjunction is expressing that for x1, that we can expand this set as x1, not x2, as an instance, comma, x1, not x1, x2. So if you say this one, x, this not x2, and remove them from this set, you still come back to this. But because we are expanding, we say this is equal to x1 or not x2, and not x1 or x2. Now we are now bringing the conjunctive operator there. So this will mean that if x1 equals to x2 is true, then this C is going to be true, because now we are saying x1 equals to x2. If it is true, then this condition even here will be true. But the problem is that the expression x1, x2, x1, not x2, and not x1 cannot satisfy the problem that is defined in the class of U. So, and that's why we say this is not x1, or is a logical form, and or is the logical and. So what we have is that we have just said that for such a problem, this kind of problem is called the CNF satisfiability, since the expression is in CNF. But why is it in CNF? If an expression of this form, I can be guaranteeing in this form that is not satisfiable, is in CNF. So CNF is conjunctive normal form, which is the product of sums. So when you look at the quotient, we have a property that explains for this very interesting analogy. Imagine there is a lemma and there is a theory. A lemma is a proposition that has not been transformed into a theory by efficient proof, or is given as a property. So this is a lemma, which stands as a property. If L1 and L2 belong to NP, L1 is NP complete, and L2 L1 when transformed to L2, then L2 is NP complete. We say L1 is NP complete. However, if this transformation exists, then L2 will also be NP complete, because this L1 has been transformed to L2. Therefore, NP, and for all other existence of NP prime are all elements of NP, and thus the same apply for the transformation of the elements that are not in the class of L and are transformed to L1, and those of L1 and L2, such that those that are not in L1, because they have been transformed, this one has been transformed to L1, and L1 has been transformed to L2. So this one is now transformed to L2. So if you look at the space here now, this is the set space. L prime is transformed to L2. So the NP, the class of problem that can define this would be that this L prime has been transformed to L2, which is given here. L prime transformed to L1, and L1 transformed to L2, such that L prime is given to this. It's quite simple. What we have done is that this one comes to this one comes to this one comes to this. It means that whatever you have here already came from this. That's why we have that L prime comes to L2. So last but not the least, so now we have to prove this problem L to be NP complete. We need to showcase the following. We show that L is in NP, and we select a non-NP complete problem that is not a decision problem. Then construct a polynomial time transformation F from L prime to L. And we prove the correctness of F, which is the transformation. That is, L prime has a solution if and only if L has a solution. This L prime will have a solution because we have transformed the L prime to L prime to L, and for the L prime to L using this polynomial time transformation denoted as L and used as this symbol in this preceding slide. So the correctness is proven, and therefore that gives us the polynomial transformation expression for the given set. So, as a summary of the class, rounding up, decision problem solved by deterministic algorithm in the polynomial time. Any problem in that category, deterministic algorithm in polynomial time, NP. Problems always be problem, including all of the ones we have discussed, such as 0/1 addition, have an additional important property, and this is the fact that if any of them can be solved in a polynomial time, then they say all can. This problem are called NP complete. It can apply to all of them. But a central point here is that it can be NP must exist. Look at it very clearly here. If any of them can be solved in polynomial time, because solving is that those that are solving the polynomial time with deterministic algorithm, those are solving polynomial time with non-deterministic and class NP. If one can be solved in polynomial time, including the satisfiability, the longest side, the nav side, all of them, then it means that all of them can be solved in that NP complete framework defined as part of the problems in NP complete. On that note, I give you the assignment for today, which is the fact that proof dilemma as postulated by Cook. Proof dilemma as postulated by Cook in the Cook's theorem. Proof dilemma as postulated by Cook. If you have questions, you can please send your questions to me. But I quickly take that before I end this class. And on that note, I thank you for being part of this session. It's good to have had all of these sessions with you. We'll be taking further notes, and you'll be having further directive as how the class will go on. So you can send your chat if you have messages. The lecture is again on YouTube, and at any time you can just visit the page and they have a